Hello, greetings to Dr. Fabia. My name is Aruni and my matrix number is SIN3005. Today I'm going to be talking about how to solve a system of differential equation with the help of Euler method. So here we have the question on top. We have dx dt is equal to 2xt plus yt plus minus t plus 5t squared plus t cubed with the initial conditions x naught is equal to 0. And we have dy by dt is equal to xt plus 4y plus t squared minus t cubed with the initial condition y naught is equal to 1. So we've been given the step size h is equal to 0.3, and we have to compute the value at t is equal to 1.5. So this is the Euler method equation. yi plus 1 is equal to yi plus h fxi yi, where h is equal to xi plus 1 minus xi. So we first have to put the differential equation into a vector notation that we have here. X is equal to x naught, x1, x2, which is equal to txy, and we differentiate this, which is when you differentiate x naught, which is t, you get 1, and you differentiate x1, which is dx dt with respect to t, and you get this, and you differentiate x2, which is that equation, you get this, and then we set x naught is equal to s, and x naught is actually 0, 0, 1, and we do the first iteration where you input, you substitute the values 0, 0, 1 into this fx, so you get 1, 1 for the vector. And for our first iteration, it's t1 is equal to 0.3, and your x1 is equal to 0.3, 0.3, and 2.2. Then you use these values to compute your t1 x1, and gives you this vector 1, 2.977, 9.163. And then for your next iteration, you get x2 is equal to x1 plus h f t1 x1, and you get this value when t is equal to 0.6. Okay, for our iteration 3, we have t3 is equal to 0.9, and our x3 is equal to this value, and you substitute this into your fx function, and you get this vector. And your iteration 4, where t4 is equal to 1.2, and you calculate your x4, you get this, and your fx function, when you substitute the values, you'll get this vector. And your t5, which is 1.5, you'll get x5 as this vector. And finally, we can see that t is equal to 1.5, our xt will be 27.175579, and our yt will be 60.322521. Thank you.
Hi, my name is Gan En Sun, and my matrix number is SIM160013, and our group use Excel to verify our answer for this Euler method. So the step size for this is h equal to 0.3, and the s naught equal to 0, 0, 1, and the Euler method formula is xi plus 1 equal to xi plus h f x naught s1 x s2. Then we start our first iteration. S naught equal to 0, 0, 1. Then we plug in the value into the formula here. Then we get 114, which is the same as our manual calculation. And at last we get S1 equal to 0.3, 0.3, 2.2. And the Y1 for our first iteration is 0.3. And then we do our second iteration, we repeat what we did for our first iteration. We sub in the value for S1, 0.3, 0.3 and 2.2, and then we get our S2 equal to 0.6, 1.1931 and 4.9489. And then we continue our step to third iteration, and we found our x3 equal to 0.9, 3.81843, 11.2887. And then we continue to our fourth iteration. We continue to our fourth iteration, and then we repeat our step earlier, and we get x4 equal to 1.2, 10.659801, 26.004991, and we continue to our fifth iteration. So we proceed to our last iteration, and we continue with our step earlier, and we get our final answer x5 equal to 1.5, 27.175579, 60.322521. The final answer is same with our manual calculation, and we claim that our manual calculation and Excel calculation is the right answer. That's all for my part. Thank you.
Good evening, I'm Chengi. I'm Neo Chengi. My matric number is SIN3005. So in the next section, we will talk about our effort in finding the exact solution to the ordinary differential equations without considering the initial conditions. So although it is unsuccessful to find the exact solution to the differential equations with the initial condition, but we did showing something. So first of all, we try our luck in finding let's say the solution is in polynomial of some finite order. So first of all, from the differential equation itself, you know that the equations, the exact solution cannot be the order that's smaller or equal to 2, because you have an x cubed there. So if the solution is x squared or below, then you cannot cancel out the x cubed, then leaving the differential equation having the higher power than the exact solution. So what is left out is when the k is greater or equal to 3. So first I'm showing that if k is greater than 3, this is just doing the simultaneous equation. If k is greater than 3, then let's say that x is in the form of nkxk and y is in the form of nksk. This is taking the summation. And first of all, the x and y must have the same order, because if x and y is not having the same order, then you cannot cancel out the highest order. So leaving the highest order in the differential equation, and you also eventually reach that the differential equation having the same power with the exact solution, which is also what we not desired. So doing the simultaneous equation, we will reach that if k is greater than 3, then mk and nk is equal to 0. So that means if you have the x power to the power of 4, then that means the coefficient is 0. So what is left out is when the k is equal to 3. Then also the same thing, you're doing the simultaneous equations. So we will reach the coefficient for the n3, which is equal to 3 over 7, and n3 is equal to negative 5 over 7. So this is the coefficient for the x cubed, and then you can proceed just like proceed with the same kind of fashion. Doing the simultaneous equation, we will find out each coefficient for x squared, x, and the constant term. So doing all the thing, you will find out that the coefficients for the polynomial of order 3 is false by doing the simultaneous equation. So you will reach the answer of x to the something something something. Yeah, it's quite complicated. The solution of x and y, if you put it into here, you can actually find out that it is the dx dt is actually equal to this one and equal to this one. So, but sadly, this is even though it's satisfied for the dx dt and dy dt, and from just now what you see is that that solution is without considering the initial condition. So you take into account the initial condition, you will find out that the answer is not consistent. So that means the answer is, if the exact solution is as this, so it must not in the form of polynomial of finite order. So that's all from me. Thank you.
Yeah, my name is Ng Wei Li and my metric number is SIN3005. So in order to get a better approximation, we try to reduce the step size from 0.3 to 0.1. And when we use the step size with h equals to 0.1, we can get these values of x and also the value of fx. And since our step size is 0.1 and we need to get the value, approximate value at t equals to 1.5, so we have 15 iterations. So after all of the calculation, we get that for step size equals to 0.1, the approximation is actually x is equals to 93.0033 and for y is 213.76. Actually, this makes a very large difference to the answer we get in front with the step size equal to 0.3. You can see that with step size equal to 0.3, the x is only 37 something and the y is 60 something. So we can know that while we are using the step size equal to 0.3, the answer is not accurate as we use the step size equal to 0.1. So next, we try to reduce the step size again to 0.05. And since we are finding t equals to 1.5, so when we use step size h equal to 0.05, we will have 30 iterations. So these are the values we found. Yeah, so at the end, we will get the approximation of x at 1.5 is 150.848 and for y is 351.424. And we think that this is a more accurate answer compared to the step size with 0.3 just now. So thank you.